In this lesson, we're going to continue to look at word problems and how they relate to linear inequalities, how solutions can be represented on a graph, and basically how those all relate to each other. We're going to do one problem and look at the key ideas. This is section 6.3 if you're one of my students. We're looking at problem number 3. And this says, a sloop is a sailboat with 2 sails, a mainsail and a jib. So it's a sailboat that has 2 sails, and they have different names. When a sail is fully out or up, it is said to be out 100%. When the winds are high, sailors often reef or pull in the sails to be less than their full capability because they don't want to tip the boat over. There's two constraints here, and I've highlighted them. It says Jim is sailing in winds of 22 knots, so he wants no more than 80% of the mainsail out. So that's one constraint. He doesn't want his mainsail out any more than 80%. And here's his other constraint. Jim also wants more mainsail out than jib, so his mainsail has to be out more than his jib. So what the question is saying is write a system of inequalities to represent all the possible combinations of mainsail and jib that Jim can have out, and then represent the solution set on a coordinate plane. I'm actually going to skip. I'm going to first of all represent this non-mathematically, just by talking it through. I'm going to skip that red part where it says write a system of inequalities. Let's just jump straight to the graph having to do with the constraints. So what I've done is let J represent the percent that the jib is out. Those are the two things we're comparing, is the jib and the mainsail. So I've decided to call the y-axis the jib axis and the x-axis the mainsail axis, and these are the percentages that they are out. So let's look at the blue constraint. No more than 80% of the mainsail is out. The boundary line would be exactly where 80% of the mainsail is out. So you just don't worry about that no more at the moment. The boundary is where 80% of the mainsail is out. If we can find 2 points where the mainsail is out 80%, we have a boundary line. So there's a point right there where the mainsail is out 80%. And you'll actually find that all of these points, you don't need all of them, but all of these points are where the mainsail is out 80%. So you could choose any 2 of those points and you've got yourself a boundary line. The next thing to consider is that boundary line inclusive? Are you allowed to have exactly 80% out? If it says no more than 80%, that means yes, you are allowed to have 80%, which then means that your boundary line is going to be inclusive, or solid, in other words. Lastly, we need to find out which side of that to shade. If it says no more than 80% of the mainsail out, you could take any of these points. I mean, I could ask myself, is this point here no more than 80%? Well, it's 30% of the mainsail out. I'm just choosing a point at random. Yes, that point is no more than 80%. So if that's a yes, then this entire left side, or the side to the left of that boundary line, is our solution, represents all the possible combinations where the mainsail is no more than 80% out. Okay, so that's our big idea right now. Now what we're going to do, and I might start shading this a little bit more loosely, is look at the second constraint. The second constraint says, so you get the idea here, the second constraint says that he wants more mainsail out than jib. So the boundary line would be, since if we take out the word more, it would say basically where mainsail is exactly the same as jib. So if it says more mainsail out than jib, I want to know the boundary where mainsail is exactly the same as jib. And that would be, there's plenty of points. We're looking for a boundary line where the mainsail is exactly the same as the jib. I mean, here's a point here. Where mainsail is 0, jib is 0, that's exactly the same. Or where mainsail is 10 and jib is 10, there's another point. There's a whole bunch of points along that line where mainsail and jib are equivalent to each other. Now, is that allowed to be included? Are we allowed to have exactly the same mainsail as jib? If you read this question, it says he wants more mainsail out than jib, so they are not allowed to be equal to each other, although our boundary line would be where they are equal. But since that point where the boundary line is not allowed to be included, we're not allowed to have exactly the same, then that's going to be a dotted boundary line. So that means this as far as what we're looking at. So here's our dotted boundary line. Now, let's take a point at random. I'm going to maybe put a point right here, or a question mark I should say. Does this point where there's 40% jib and 10% mainsail have more mainsail out than jib? The answer to that is no. And what you'll notice is that a point on this side, here's a mainsail of 30 and jib of 10. this side would have more mainsail out than jib. So this side would be a yes, which means in turn that we're going to shade this side, or the lower side, if you label it the same as me. If you label the vertical axis as the mainsail and the horizontal as jib, it would be the exact inverse of this coordinate set. But you have the same representation of your answer. So there is that overlap green part represents all the possible combinations. So for example, if we look at this point here, this would be no more than 80% of mainsail out, as well as more mainsail out than jib. Also, this point here would be no more than 80% of mainsail out, but more mainsail than jib. Those are the two constraints. So those are all the representations of solutions. The last thing that we should recognize is you can't have a negative amount of sail out. So those negative quadrants aren't included, but you don't need to have integers out of your mainsail. You could have 49.5% of your mainsail out if you'd like to. So that's representation. This green triangle here, just highlight it for you, that represents all the possible combinations of mainsail and jib. Now, if we'd like to actually use a system of inequalities to do this, it's totally possible. It would look like this. According to our blue constraint, no more than 80% of mainsail out. That would be that mainsail has to be less than or equal to 80, and you get the boundary line would be where m equals 80, and you get the exact same vertical boundary line. So you can see you get it the same way, and you'd also shade below it, so the exact same graph of that inequality. With more mainsail out than jib, that would look like this. Mainsail is greater than jib. You'd get the exact same boundary line because it's where m is equal to j. So if I put in m equals 0, I'd get j equals 0. That would be this point here. And if I put in m equals 10, then j equals 10. That would be this point here. So you get the same boundary line, non-inclusive, and you'd shade below it if you used a test point. So it's exactly the same representation. But this would be with this, using a system of inequalities, or you could use it the non-mathematical way. You get the same representation of all the possible combinations. So lastly, just the key ideas when solving a problem involving systems of linear equalities, the first thing you should do is define the variables. So what are the two things that you are trying to find different combinations of, and label the axes. For word problems, what you should try to do, if you can, I did this backwards, so when I showed you I didn't do this first, but you could, and a lot of you might find this easier, write a system of inequalities to represent the constraints of the situation. Step 3, graph the solution region for the system of inequalities, and you can see the 6.1 and 6.2 notes. Keeping in mind a few things. First of all, if the boundaries are solid or dotted, so included or not included in your solution, then you should also use a test point to determine which side of the boundaries to shade. And finally, you need to consider the restrictions for the solution region. So can your answers be anything? Are they restricted to just integers? Or are they restricted to whole numbers? Lastly, the non-mathematical way I've written here. If you can't do step 2 is coming up with a system of inequalities. So that would be if you can't come up with these inequalities that I've written here and here, or for the problem in the last lesson, these two inequalities. If you can't do that, what you could do is do it the non-mathematical way, which is graph the boundary lines from the word problems itself by removing any optimization language. So take out the word more, less, at least, no more, maximum, or minimum, and you can find out your boundary, and you only need 2 points to graph a boundary line. Then you should shade the appropriate side of each boundary line by considering the optimization language. So consider which side of that represents the more, less, at least, no more, maximum, or minimum. And finally, consider any restrictions.